Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this video, we're going to be learning about the ideal gas law. We learned about a number of other simple gas laws in previous videos like Charles' law, Boyle's law, and Avogadro's law. Well, now we're going to see how all the variables, your pressure, your temperature, your volume, and the number of moles are all interrelated in one equation. Let's get started. But as I mentioned, we can actually combine all three of the gas laws into one simple equation that relates all of the different variables. And so just to recap, remember our Boyle's law showed that there was an inverse relationship between pressure and volume. Our Charles' law showed us a direct relationship between volume and temperature. And Avogadro's law showed us a direct relationship between volume and moles. A great way to remember all these are those mnemonic devices. So I'll say them one more time for you here. So you can remember the variables with Boyle's law by saying boil, you can boil potatoes and vegetables, so P and V. Charles' law, remember Charles Barkley is very tall. And so that's a great way to remember the volume and temperature variables. And then Avogadro's law, avocado kind of looks like avocado. Avocados are very nutritious. So very volume, nutritious is your moles. Well, now when we put all of these together, we can develop this equation, which is known as the ideal gas law. And the ideal gas law incorporates your pressure, the volume, the moles, and the temperature, and shows how they're related by utilizing a gas constant, which is the symbol R. And so this is really great when we're trying to assess or find information about a certain set of conditions based on the variables that are provided for us. So a big thing that we need in these types of problems is we have to make sure we're incorporating the appropriate gas constant. Again, a constant is something that, as the word implies, is constant. So regardless of what type of gas we're thinking about or looking at, that constant will remain the same. So this gas constant that we're going to be used has a value of 0.08206 atmospheres times liters divided by moles times Kelvin. And so what that means is we have to be in specific units for this to work. Your pressure has to be in atmospheres because that's what's found in our gas law, our gas constant. Your volume must be in liters here. The moles will of course be moles. And your temperature has to be in Kelvin, okay? So we have to make sure that we are in the appropriate units to be able to utilize your ideal gas law, okay? And so this is often referred to sometimes as the Pearson equation. So you may hear some people talk about that, but it's simply your ideal gas law. Okay, and really this is the foundation for having or being able to develop those simple gas laws, because if we're able to say that they are equal to this constant, right, the pressure times the volume divided by the moles times the temperature, well, we can use that to come up with this expanded ideal gas law that would show original versus final conditions, and from there we can develop those simple gas laws. Okay. And so if you're trying to do or trying to derive those simple gas laws, your pressure, your Boyle's law, your Charles' law, or Avogadro's law, then you simply can take this ideal expanded gas law and actually derive those things by holding variables constant. So if a variable is held constant, that means it's the same value on both sides, which means mathematically it would cancel out. So for instance, if we're saying we're looking at Boyle's law, well, that means that that means that temperature and moles are held constant. And so they would fall out of the equation. And that's where we get our Boyle's law. If we're saying that pressure and the moles are held constant, that would give us now V1 over T1 equals V2 over T2, or Charles' law. And if we're saying that the pressure and temperature is held constant, drop them away. That gives you your Avogadro's law. And one law that I didn't do a video on, but that does exist, is Gay-Lussac's law. So Gay-Lussac's law is looking at the relationship between pressure and temperature. That means volume and moles are held constant, so that drops away. And you're left with P1 over T1 equals P2 over T2. So really, if you know this expanded ideal gas law, you actually know all of the other simple gas laws, and you can derive them. All right. So another concept that we want to be familiar with is standard conditions. And so because there is this constant that we can refer to, there is a set of conditions that we can easily report out based off of a series of measurements that have been done. Now, those standard conditions are what we call STP, your standard temperature or standard pressure, are shown for you here. So your standard pressure will have a value of 1 atmosphere. So anytime you see that, you know you're at 1 atmosphere. And your standard temperature would be 273 Kelvin, or 0 degrees Celsius, okay? And so that's just a quick way to reference these values by just saying you're at STP. And as such, if you're at those particular pressure and temperature, that means the volume and mole amount could also be predicted, assuming that you're at those pressures, those pressure and temperature. All right, so let's jump into a problem. And so it says, how many moles of gas are in a basketball with a total pressure of 24.3 psi and a volume of 3.24 liters at 25 degrees Celsius? Now, when you're doing this, you want to think about, well, which equation do I want to pick? Because there's a lot of equations we've covered so far in these few videos that I've done. And so a great way to think about it is, well, am I looking at a set of conditions, or am I looking at, some starting conditions and then going to some new conditions? So depending on what you're looking at, that will tell you which equation you want to use. So let's look at what information we're provided. So it says, how many moles of gas, so we know we have an N, are in a basketball with a total pressure of 24.3 psi and a volume of 3.24 liters and a temperature of 25 degrees Celsius. Well, in this particular case, I don't see where it says my volume is changing from this to this, or my temperature is changing from this to this. So it's pretty certain that I would be able to use our ideal gas law to solve this problem, because it helps me to relate all of these different variables. So we then have to take a look at, well, can I just simply plug in to solve this problem? And you should be having some red flags that are going off that says, no, I don't have the appropriate units. Remember, for the ideal gas law, you have to be in atmospheres for pressure, liters for volume, Kelvin for temperature, and then moles for moles. And so our pressure and temperature right now are not meeting that criteria. So before you start plugging in, go ahead and rearrange or convert to the appropriate units. So we would take 24.3 psi, and we are going to utilize the fact that there are 14.7 psi's for every 1 atmosphere. And so when we plug that in, we have 24.3 times divided by 14.7. And that gives us 1.65 atmospheres for the pressure unit. And for my temperature unit, for our temperature unit, we would actually need to convert from Celsius to Kelvin. So we see that we're at 25 degrees Celsius. We would need to add that 273.15 to get us to our Kelvin unit. And so that would give us 298.15 Kelvin. And again, we can drop off that 0.15 because of sig figs. And so that's what we're going to plug into our calculation. So now when we look at our equation, we want to rearrange again to solve for our desired variable, which is N. So we would divide both sides by RT. So we would end up with PV equals R over T. And so now when we plug this in, we have our pressure unit, which is 1.65 atmospheres. We have our volume, which is 3.24 liters. Our R, well, you don't see R listed, but you have to remember that's a constant. And so that would be 0.08206 liters times atmospheres divided by moles times Kelvin. And then our temperature unit is 298 Kelvin. Now be careful when you're putting this in your calculator. Make sure when you're putting the stuff on the bottom, make sure if you're going to use a multiplication symbol between the 0.08206 and 298, you got to put all that in parentheses. I always just recommend my students to hit the divide button both times. So you should be putting in 1.65 times 3.24 divided by 0.08206 divided by 298K. And so when we do that, we end up with a value of 0.219 moles as our answer. Okay. All right, next up. It says a gas occupies 10 liters at 44.1 psi and 27 degrees Celsius. What volume would occupy at STP? So we learned about STP before, so let's look at what we know. So we have a volume at a pressure and a temperature. Well, then it's saying, well, what volume will it occupy at standard temperature and pressure? And so that means we have a new temperature and a new pressure. So there's a change. We're going from one set of conditions to another. And so what that tells me is that we need to use some version of the ideal expanded or combined gas law to allow for that. And so that combined gas law tells us that P1V1 over N1T1 equals P2V2 over N2T2. Now, what we don't see mentioned in this problem is moles. And so we can actually drop that out of our equation because we can assume that it's being held constant. So now we're ready to think about what we would have to rearrange in order to solve for this problem. And so it's telling us that we want to solve for the new volume. So that means that we're looking for V2. So if we rearrange the equation, V2 would equal P1 times V1, now times T2, because we're going to bring that T2 up. And then we're going to divide it by T1 and P2. We're bringing this P2 down. So bringing this down, bringing that up for your rearranging, okay? Now, before we plug in, we got to make sure that we are in the appropriate units. Remember, they have to match on both sides. And so I need to convert my temperature and my pressure to the proper units. So I'm going to first take my PSI, my 44.1 PSI, and we're going to convert to atmospheres, to 1 atmosphere. And then also we are going to do our our temperature to Kelvin, so 27 degrees Celsius plus 273.15, and we'll plug in both of those calculations. So we have 44.1 divided by 14.7, and that gives us a pressure of 3 atmospheres. And for our temperature, we have 27 plus 273.15, and that's going to give us 300.15 Kelvin. Again, we can drop off there. Now, when we plug in, we would take our P1, which is this now converted 3 atmospheres. And then we're going to take our volume 1, which was 10 liters. Now, T2, remember, it's telling us we're at STP now. So that means T2 would be 273 Kelvin. Our T1 is what we've converted, so that's the 300 Kelvin. And our P2, remember STP, that means we're at 1 atmosphere. And so we'll plug it in, 3 times 10.0 liters times 273 divided by 300 gives us 27.3 liters. And we can see that it's liters because of atmospheres here and kelvins are crossing out here. Okay. For this next problem, we're asked to calculate the volume occupied by 637 grams of SO2 at 6.08 times 10 to the third millimeters of mercury and negative 23 degrees Celsius. So if we look here, we're looking to solve for the volume, and we have a mass. We also have a pressure and a temperature. Again, notice in this problem, it's not going from one variable set to another variable set. It's basically saying we're at these conditions, figure out what information, or find this variable. And so when we think about this, we likely are going to just need to use the Pervnerd equation, or PV equals nRT. And so with that, we're going to need to remember that we have to actually do some conversions before we can plug in. our pressure has to be in atmospheres. So let's go ahead and convert that. 6.8 times 10 to the third millimeters of mercury. And what we're going to do is we're going to use the conversion of 760 millimeters of mercury and 1 atmosphere. And so you get 6.08 e to the third divided by 760. And that gives us 8.0 atmospheres. For our temperature, we have negative 23 degrees Celsius. We're going to go ahead and add 273.15 to that for our temperature. So negative 223 plus 273.15, and that would give us 250.15. Again, we can drop off that decimal point for our Kelvin. Now, notice one thing that seems to be missing from this problem, if we want to use that PV equals nRT equation, is the mole amount. However, we do have this mass that's given to us, and we know from previous videos that we can convert from grams to moles very simply by using the molar mass. So let's go ahead and do that conversion as well. So 637 grams of SO2, and we're going to put our molar mass, which they've provided for us. If that wasn't given to you, you would just simply look at the periodic table and calculate it, and 1 mole on top. So 637 divided by 64.07, and that would give you 9.94 moles of this substance. So now we're ready to plug in. So we would take our equation and rearrange to solve for volume. Volume equals the moles times R times temperature divided by the pressure. And then we're going to now plug in all those values that we've recently converted. So we would put 9.94 moles here, our constant of 0.08206 liters times atmospheres divided by moles times Kelvin, and our temperature of 250 Kelvin. And we're going to divide all of that by our pressure of 6.08, make sure we put the converted pressure in, our 8.0 atmospheres. Now, when we plug this in, we got 9.94 times 0.08206 times 250 divided by 8, and that gets you 25.48 or 25.5 liters as our final answer. Okay, so make sure you're doing all those conversions and plugging in the proper number. And then one last problem. It says a gas takes up a volume of 17 liters, has a pressure of 2.3 atmospheres, and a temperature of 299 Kelvin. If I raise the temperature to 350 Kelvin and lower the pressure to 1.5 atmospheres, what is the volume of the gas? So again, go through and figure out what we know. We have a volume, we have a pressure, we have a temperature. Well, then it says, well, if I raise, so that means I'm changing the condition. So all of those first variables, I'm going to call that V1, P1, and T1. And then it says, I've raised my temperature to 350, so that's T2, and my pressure has changed to 1.5, so that would be P2. So what we're solving for is V2. And so again, since we have this starting in certain set of conditions, changing to new set of conditions, we now want to make sure we're using the appropriate equation, which would be that expanded ideal gas law. So P1 over V1 equals N1 over T1, and that's equal to P2 times V2 divided by N2 times T2. Now notice moles was not mentioned in this problem, so we can assume that it's held constant, and so that can drop out of our equation. We do a quick scan of all of the units and they look to be appropriate. So we get ready to just go ahead and rearrange. So our volume would be equal to the pressure P1 V1 times T2 divided by T1 times P2. So again, all I'm doing to solve for V2, I'm bringing that up, bringing that down to isolate our volume. Now we're ready to plug and chug. So P1 is 2.3 atmospheres. V1 would be 17 liters. T2 would be 350 Kelvin. T1 would be 299 Kelvin. And last but not least, P2 would be 1.5 atmospheres. So when we plug that into our calculator, we're going to do 2.3 times 17 times 350. Now divided by 299, divided by 1.5. I think I missed a number there. Let's insert my 299 and 1.5. So when we plug that in, we end up with a value of 30.5, and this would be liters because atmospheres have canceled, kelvins have canceled, as our final answer. I hope this video helped you to understand the ideal gas law and the expanded ideal gas law and how to solve problems appropriately. Make sure you guys like, comment, and subscribe, and let me know what other content you want to see. Be sure to check in for more videos related to gas laws and other general chemistry topics in the future. Have a great day, and I'll talk to you guys later. Bye-bye.